Time is up. So, hello everyone. Thank you for joining our sessions titled Dependency Injection for On-Device AI System. In this section, we will explore the engineering challenges we faced when applying the on-device AI to consumer electronics and shares our journey of how to solve them to launch the commercial product. Before beginning, we'd like to briefly introduce ourselves. I'm Sangjung, and I'm a software developer at Samsung Research. I also contribute to the open source project NNStreamer and Tizen.
Hi, my name is Abha. I'm working in Samsung Electronics. I work as a NPU, SDK, and driver engineer.
Hi, I'm Jinhwi. I'm software developer at Samsung Electronics. I'm MPU SDK developer in digital appliance team.
On-device AI is already embedded in many of the products you use every day. Unlike the cloud AI, on-device AI means the AI application runs directly on your device with no network connection required. However, computing power on the device is limited. Therefore, it requires sophisticated optimizations for each specific device. The benefit of on-device AI are clear. Because no data is sent off the device, it provides excellent data privacy. It doesn't require the network connection, which achieves the low latency. Additionally, for devices that support retraining, we can apply personalization, allowing the model to adapt it specifically to users. Last but not least, for the service providers, applying on-device AI can significantly lower cloud operational cost. On-device AI models are developed as the following procedures. In the preparation phase, we define AI tasks and collect and process the data. In the training phase, we design and train the model using standard machine learning frameworks like PyTorch. In the optimization phase, we perform the optimization, such as quantization, to improve inference speed and reduce memory usage. After that, we converted the model for the target hardware accelerators. In on-device validation phase, we verify the converted model's accuracies and measure the performance metrics. Finally, the validated model is packaged for deployment. However, to achieve optimal performance, we must consider the target accelerator right from the optimization phase. This is because every hardware accelerator is different. They all varied in their vendor-specific toolkits and runtime support, their supported operations, quantization build-width, quantization unit, and scheme. General-purpose frameworks like TensorFlow Lite or Onyx Runtime offer the broad compatibility to run on various hardware accelerators. However, they have limitations in delivering the peak performance that vendor-specific toolkit can provide. For these reasons, when applying the on-device AI, our product, we faced the following engineering challenges.
We experienced various engineering challenges during development. First, API fragmentation. To provide better service, we had to check various vendors' APIs every year, and when a new hardware vendor was added, due to different SDKs for each vendor, AI model developers and app developers had to create new samples every time and provide them. Second, complexity of resource optimization. Measuring memory usage, ensuring real-time latency, optimizing power consumption, except each vendor provided benchmarks, but in reality, when the model was running on board, the results often differed, making it difficult to verify. Third, frequent model updates due to AI advancement. AI is advancing rapidly, and as a result, the model life cycle is short. Therefore, we had to update VLTA. Additionally, rolling back and deploying when issues arose was also challenging. Fourth, stabilization of maintenance. Most home appliances are used for a long time. In some cases, they are used for up to 10 years. Therefore, we guarantee 7 years of OS updates, and accordingly, we had to continuous support update for other components as well. We compare the APIs of various vendors, and if they offer a better environment, we verify and use them. However, as briefly mentioned earlier, there were many issues. The SDKs of all vendors are different, and each SDK is locked to its respective vendor. When updates to the SDKs are made requiring changes or additions to the calling code, both app and model developers have to adapt to these changes, making maintenance difficult. Keeping up with all these code changes was very time-consuming, making it challenging to update promptly. Writing test code for resource verification and ensuring that we meet our desired KPI also took a significant amount of time. Furthermore, the advancement of AI and the demands from users are progressing faster than the upgrade timelines for basic applications or OS. Therefore, than the upgrade timelines for basic applications or OS. Therefore, we wanted to update the AI model more quickly and bring it to the market. But since the update cycle differed, the update schedule was aligned with the slower side. Additionally, to utilize the new layer added to the AI, we had to request an SK update from the vendor, receive it, recompile the model to make it usable on the board, and then redistribute. In such case, model developers and app developers faced inconvenience as they had to branch their app codes according to the SDK version. Lastly, home appliances are generally used for a long time. As a result, issues arise over time with numerous hardware changes and additions, and in some cases, the hardware used long ago is no longer supported by vendors through SDK updates. In such case, we realized that new developers would need to spend too much time and effort figuring out the entire previous environment and then developing and adding features to match it. However, we want users to continue using Samsung products for an extended period and to have their product experience improve through updates during that time. To achieve this, we decided to provide OS updates for the next 7 years to ensure there are no issues with product usability. And we have put a lot of thought into how to approach this from a software perspective.
Okay, let's discuss architectural approaches. The AI application is dependent on hardware accelerator, machine learning frameworks, and platform and models. First, when the hardware accelerator changes, AI application requires optimization work specific to that accelerators. As the number of accelerators we must support increase, the complexity also grows rapidly. Second, in terms of a machine learning framework, we have not only standard runtime like TensorFlow Lite, but also proprietary runtimes that vendor provided. When the runtime changes, there is no API compatibility between them, and this forces application code changes. Finally, the platform is updated. It can cause application compatibility issues on existing product. Furthermore, the fast update cycle of the neural network model lead increased validation time for AI applications. To solving these dependency problems, we apply the dependency injection techniques. This means that we logically separate AI applications from the hardware accelerator, machine learning framework, platform, and model by injection these dependencies externally. Through these approaches, application developers can write their code against the predefined standard interface without being aware of the specific hardware accelerators or machine learning frameworks. Model developers can also use a JSON configuration file to define specialized settings. As a result, the AI backend can be changed without any modifications or rebuilding of applications. Finally, physically separating each component into distinct packages and layers, it is possible to update them independently without impacting one another. Then let's look at the detailed implementation. To support the various hardware accelerators and machine learning framework, we adapt NNStreamers. NNStreamer is an AI pipeline framework based on the GStreamers, which allows the AI model can act as filters. This project was already released open source, and it is one of the LF AI and data project. The way NNStreamer works is as follows. It defines the standardized tensor format that follow media data to be used for neural network operations. It provides a converter element to transform media data into tensor format. The filter element that execute the AI model using hardware accelerations, and decoder element that convert the inference result into metadata format. By combining these elements, including GStream element, complex AI application can be written with just a few lines of script. To support the barrier hardware accelerator within NNStreamer's filter element, we adapt a plugin architecture based on the open-close principle. This means that we define a standard interface for neural network operations, which is allowed each hardware accelerator to be extended its own corresponding plugin. We also designed it so that the specific settings can be passed as key value pairs. This allows us to achieve the best performance while still using the standard interface. This implementation provides several key benefits. First, we can rapidly support the new hardware accelerator without impacting the existing implementation. New developers can add a new plugin using less than 800 lines of code within a month. Second, each plugin module is a shared object, so it can independently update it and deploy it. And lastly, we can integrate the plugin from proprietary vendors as a closed source, which allows them to keep their code private. This example demonstrates how to perform the real-time object detection using NNStreamers. As you can see, the video feed from the camera is split, and the bottom part performs the neural network operations. The inference is processed through the converter, filters, and decoder element we discussed earlier. In this example, we are using the TensorFlow write runtimes with MobileNet SSD model. The inference result and the original video streams are combined in the compositors to display the recognized result, as shown here. If you were to write this entire process in code, you would have to write the significant amount of code. With NNStreamers, you can implement the core functionality of AI application with just a few lines of pipeline script. However, the pipeline script is passed as a function parameter directly inside the application code. In the next slide, we will discuss how we solve this problem.
Next, I want to talk about a major challenge we faced in AI model deployment and how we solved it with our configurable ML APIs and model packaging. Due to current implementation design, model deployment suffered from tightly coupled code. It created a monolithic deployment where everything is packed as an inseparable unit, and which is called an app package here. We had to develop applications that performed the same function but had significantly different code bases. This was because we needed to support AI models across both entry-level and high-end devices which had variations in NPU vendors. In the current implementation, the ML engineers and the app developers were always dependent upon each other. As you can see in the figure, they have to work in sequence, not parallel, which led to create various bottlenecks. Updating a model required a full app update, meaning even a small AI change need to do a complete redeployment of app package. It resulted in higher maintenance costs and a slower innovation. Every change requires coordination between both the teams, delaying improvement and increasing the expenses. Our solution addresses all these challenges. We focused on eliminating the dependencies among modules. Our configurable ML API removes the tightly coupling between the app code and the AI models, creating a flexible interface that works across the ML frameworks. Using the dependency injection principle, we provided a runtime model configuration externally to applications using the config file. This helped manage all the model-specific requirements, metadata, and dependencies separately for various devices. Application became truly model agnostic, that is ML framework independent, and are able to run any AI model without any changes. For instance, whether it's using a TensorFlow TF-Lite or a different vendor-specific AI backend. As shown in the figure 2, we decouple the app and the model packages with the help of Tizen resource package. By splitting them into independent units, during the development phase, different ML engineers can take care about the development of model 1 and 2 for different devices simultaneously. App developer need to work on only one single application capable to run and use different ML frameworks and model formats for both entry-level and high-end devices. Models can now be updated, versioned, and switched to use ML frameworks easily, which enables parallel development of app model and the application by different engineers. As shown in the figure 3, you can see in the update phase that only we need to update the model package and the rest of the application remains same. This configurable approach transforms AI model deployment from a monolithic challenge into a modular, flexible system that adapts to changing needs without disrupting the entire application. Let's look at the actual use case scenario in a bit more detail. Model packages provide flexibility for ML engineers to work independently on different models. It is divided into two modules. The first one is the model file, which is compatible to standard ML frameworks like TF-Lite or AI Accelerator by vendors like Qualcomm, VeriSilicon, etc. Second is the pipeline configuration file, which is in the JSON format that contains various runtime parameters. I'm going to highlight the main elements of this configuration file. The first one is the description, which is a mandatory parameter and specifies the details about the model. It also includes the details of the ML framework or AI accelerator to be used during the runtime. For example, we have selected the tensor filter framework as SNP for a model detection.dlc, and we can select the configuration parameters to have CPU, GPU, or NPU as the backend. Next parameter is related to the input node and the output node, where the shape of the input and output tensors of the model is provided. It's important to mention the data type and the layout of the dimension for proper buffer management of the whole AI pipeline. Last one is the optional parameter, which is used for the post-processing part of the output from the model after the inference is done. For example, this can include the threshold value for the non-maximum suppression of the bounding boxes of the object detection, or a label path file, etc. So next, let's look at the details of the model package and the ML agent. Easy model deployment is one of the key benefits of our approach. Unlike the previous methods, this provides flexibility in installation and updates of the external models. We use the Tizen resource package as our model package format, so it integrates seamlessly into the Tizen platform. This figure illustrates the process of how an external model is installed onto the Tizen. External packages are installed with the help of package manager, and in case it is found that it is a type model, then the ML agent registers it with the model repository. We feel on-device version management is a must during the model update. Certain devices can improve AI model performance through the on-device retraining. For example, in an object detection model, we can add a user-specific classes like recognizing my dog Coco instead of using a generic class dog. So we can call this feature as personalization. During this retraining process, the model may not work perfectly. To ensure the stability, the applications still continue to use the model version 1. And after the retraining and the validation is completed, a stable version is given to the model named as a stable tag, which allows the applications to safely switch the version from model 1 to model 2. Finally, if any problem arises, we can have a feature of rollback mechanism to immediately restore the application back to the model 1. Our approach also allows model to be shared across applications. In this figure, we show an example that how two applications are using the same model through the ML APIs. By default, they access the latest stable version, but they can also access the specific version if one is specified. Using the same approach, it enables the personalized models to be shared across the applications. In consumer electronics field, when developing any hardware abstraction layer, Long lifespan, long-term support, and hardware fragmentation are the major challenges. In our approach, we do decouple the dependencies between the Tizen platform and the hardware accelerator completely. You can see in the figure that our software stack consists of the Tizen platform, AI application, ML API, HAL ML APIs, and then we divided the HAL backend separately, where the ML accelerators can have their own backends for Qualcomm, VeriSilicon, and other vendors. And finally, we have the hardware, which is the actual chipset provided by the vendor. So this architecture allows enabling independent updates, that is, Tizen platform updates can be done without considering the HAL backends. Developers can focus on the app and model development without worrying about the new SDK changes. We also ensure backward compatibility for HAL modules, which allows to provide updates for the legacy devices. This actual usage slide will provide you more clarity on Tizen platform and HAL architecture. When a product is purchased, it is configured with the following software stack. As we can see in the figure, the application is running on Tizen 9.0 and having a ML API adapter at 1.0 and a backend at 1.0. In case a new version comes up, let's assume after 1 year Tizen 10 is released, it will be likely equipped with the new AI applications offering enhanced features and which would require new AI accelerators and backends to be added. Because of the new platform is designed to support both ML APIs at version 1 and at version 2, it can connect to the hardware independently and can also be released to the products which were already there in the market. This approach allows us to continuously add new features while guaranteeing that we will be able to operate it on the existing devices. Through this approach, we aim to deliver the best customer experience while simultaneously supporting the 7-year Tizen platform updates. We think this development can also impact open source community greatly. Our solution is open source, community driven, low maintenance, vendor neutral, and extensible. Our solution has standardized APIs where adding a new vendor API isn't difficult, so you can easily use our code. By creating an integrated ML APIs, we can make the maintenance very simple. App developers can solve their problem independently using the app package. AI models can be handled by the model package, and the vendors can independently work on their SDKs. It is possible to identify any problems on the specific hardware. It is flexible. Simply changing the configuration file makes it easy to compare performances across different backends. So it is also extensible. Even if the hardware vendor was added, by addition of the configuration file, connecting SDK with respect to the accelerator, we can develop new models.
Let's take a look at the AI of the products we have commercialized. For the family of refrigerator, we have developed the food recognition AI model. Currently, it has been updated to recognize 37 types of fresh foods. The refrigerator can recognize foods in real time to identify what types of food are being stored and use this information to recommend personalized recipes to users through SmartThings. User can also track which foods have entered or left the refrigerator. Additionally, a temperature change prediction model for the refrigerator has been developed. The AI analyzes the user's refrigerator door opening and closing pattern, predicts the refrigerator temperature 5 minutes in advance, and determines whether to operate the compressor or use the Peltier elements for cooling when situations such as bulk food storage or cleaning occur. This helps maintain the optimal temperature using the minimum amount of energy. Next, you can see the object recognition of the robot vacuum cleaner. By using an RGB camera, we maximize performance by minimizing latency through zero copy of the incoming image data, allowing for faster and more accurate information in object recognition. Additionally, with the continuous addition of datasets, the AI model is updated to provide better service to users. Whereas previous only object recognition capabilities exist, an algorithm has now been added to recognize pollutants and either avoid them or clean them up. Next is long and short file carpet recognition feature. Using probe detection sensor data, the system determines whether the carpet has a long or short file. According when it detects a long file, the mop is left at the station while the carpet is cleaned. For short file carpets, the mop is lifted as high as possible as to avoid contact with carpet while cleaning. The AI model we mentioned above through the ML API, we have dramatically reduced the update cycle for existing AI models. Developers can now work simultaneously on their respective tasks without waiting for front-end development stages. Enable seamless integration. This has revolutionized workflow efficiency for developing new apps or AI models. This approach eliminates the sequential issue that arose during updates and removes unnecessary code change between app developers and model developers. As a result, the time required to release a new AI model, which previously took 8 to 12 weeks, has been reduced to just 2 to 3 weeks. Unnecessary code changes are eliminated, significantly reducing the scope of rebuilding and tests required. Previously, when code changes were needed due to vendor or SDK updates, both app developers and AI model developers had to collaborate, requiring extensive testing across all areas and consuming considerable time. Now, with app and AI model developers completely separated, if only the model is updating without requiring UI UX changes, the app can verify the model without additional modification. This reduces verification time and prevents issues arising from modifications, significantly cutting down on problems and dramatically shortening development cycles. We have faced various challenges and aim to provide solutions that eliminate dependencies. First, minimize hardware dependency. Second, base each hardware configuration on JSON to eliminate the need for code modification by AI model developers and app developers. So this enables completely separate updates for the app and AI model. This approach allows faster updates with unified significance when adding new hardware vendors. Additionally, this approach significantly reduces redundant code development for app developers and AI model developers when new vendors were added, even for the same model and app. It also minimized development resource usage by allowing simultaneously development or enabling model-only updates when necessary, drastically shortening both the AI model update cycle and the app development cycle. This means more opportunities to enhance the quality of service provided to consumers in the actual market, and it has become much easier to access this service.
This is the last slide. Everything we've discussed in this section is 100% open source. Please visit our site and join us. We always welcome your contribution. Thank you.